Welcome back. Hope you guys enjoyed your weekend. A few announcements to start off. So in case you haven't been following the group, homework 1 is out. I hope you've all had a chance to take a look at the PDF. There are 3 writing and thinking questions and 1 coding question. The coding question, we're using AutoLab for submissions, which means that you get immediate gratification if you submit the right answer, and immediate lack of gratification if you don't. Since this is the first time we're using AutoLab for grading, I encourage everybody to start submitting early to make sure that there are no hiccups. We'll do our best to fix any of them, but if we discover them 10 minutes before the due time at 10:30 in the morning, well, it will be better if we discover them before that. Does anybody have any questions either on the coding part or on the other parts of the homework? Yeah.
On the coding, you're saying it's done in R. If we write everything up in MATLAB and submit it, would it still accept the same code, or will it have to be translated?
It's done in Octave, right, which is MATLAB clones. So if you write it in MATLAB, it should just work. There are a few differences between Octave and MATLAB. So if you run into weirdnesses, take a look at the Octave documentation to see if you're using an unsupported feature. But hopefully you shouldn't need to use very esoteric versions of the code to solve these questions. So hopefully there shouldn't be compatibility issues. The reason, by the way, that it's Octave instead of MATLAB is because the license server for MATLAB is very unhappy about running in a virtual machine. And so we'll try and fix that. But at the moment, we're using something that's open source and doesn't need a license server. All right, the other thing is, in case you haven't seen on the group, we've been posting our lecture videos and slides. So the links are all in the group. I should also point out that we have slides synchronized with some of the lecture videos so that you can see the slides in one part and the corresponding part of the lecture video in another. This is really cool. It's experimental, so let us know if you have any troubles. Maybe. Is that any better? OK, cool. Hopefully I stopped clipping for the content part of the lecture. All right, so review of where we were at the end of last class. We were talking about naive Bayes for binary inputs. So we had an example xi, which had a bunch of features xij. And these features were either 0 or 1. So for example, in our text classifier, we had the features be presence or absence of a word, like lottery in your email, or presence or absence of an n-gram, or any of a number of other features that we talked about. And we talked about the naive Bayes assumption. Anybody remember what the key assumption of naive Bayes is? Independence, I hear. Almost. What kind of independence? Conditional independence. Very good. So conditional independence, meaning that the different words of the document are conditionally independent given the class of the document. So for example, the probability of seeing lottery might change depending on whether it's a spam or a not spam. But given that you know the class, you know what the probability of seeing the word lottery is, and it's independent of any other words like million for $1 million. All right, and that led to a classifier. We just plugged that assumption in to Bayes' rule, turned the crank a bunch of times, and got a classifier out at the end. And the form of that classifier was pretty interesting, right? It was just a linear separator. We computed a linear function of the features of the document and tested to see whether that was bigger or smaller than some threshold. And on one side it was spam, and on the other side it was not spam. All right? So that's kind of cool, right, that you go through all of these calculations and you come up with such a simple rule for classifying the documents. Both cool from a mathematical point of view and cool from a computational point of view, because it's really efficient to go through and accumulate these. It was a sum of differences of log probabilities. Right. And finally, we talked about estimating probabilities. So that was using Laplace smoothing. Which is basically the same as counting up the number of words in the document, the number of times you see a particular word divided by the number of opportunities you had to see that word, right? Except that we were adding a little fudge factor to all of the counts so that we wouldn't get 0 over 0 when we estimated some probability, right? And so the classifier was a linear discriminant. And the naive Bayes assumption was conditional independence, which is okay. So that's where we were at the end of last class. Any questions on naive Bayes or text classification? All right, so let's onwards and upwards. The documents had binary features. What if we had continuous features? Could we still do classification using naive Bayes? So here's an example of a classification problem with continuous features. This is what's called the read the mind experiment. It's somewhat famous. The idea is that you have a subject who's in an fMRI machine. And the subject sees a word, like let's say hammer or church or something like that. And then you record the fMRI of the brain, which is, depending on what size the region is of your brain, hundreds of voxels to tens of thousands of voxels. Each voxel is about a millimeter cubed of brain tissue. And you get one real number per voxel per second, which is a proxy for the amount of activity in that voxel, how happily the neurons are sitting there busily firing. Okay? And so, this is the sort of thing that, if you're wearing a tinfoil hat, it's to keep the government from finding out this information, right? What your brain activity is like. Presumably, you would notice if the government put you in an fMRI machine, right? They're not small, but maybe they have some technology we don't know about. Okay, so you record all of the brain activity and all of the different voxels that you have, and then the goal is to classify, is the word that you're looking at a word about a tool, like hammer, or a word about a building, like, let's say, school or church. Okay? And if we wanted to do naive Bayes on this, what we would want to say is, well, each of these voxels are conditionally independent given the class. So there's some amount of activity that you would get for tool words and some amount of activity that you'd get for building words, and they'd have different distributions. And we have to make some kind of assumption about what distribution they are. And because we're in the business of making naive assumptions already, let's just assume that they're conditionally Gaussian, right? So, and so this is also a naive assumption, right? It's at least as naive as the independence assumption, but just because it's false doesn't mean it isn't useful, right? So, so what happens when we do that? We get Gaussian naive Bayes, right? And so the assumption winds up looking like this. It's that the probability of xij given yi, right? So yi is the class, and this is the voxel j in the ith example, right? And that's equal to a normal distribution with mean mu j, and then there's going to be, so there's a separate mean for each pixel, and that's going to depend on the class, so yj, right? So I've got mu sub j for the pixel, sorry, not yj, but yi, right? So it's going to depend on the class of the entire image. Comma sigma squared, so I'm going to assume a common variance for each one of the pixels, right? It doesn't depend on anything. Right? And so I have that, which is equal to 1 over the square root of 2 pi sigma exp of minus 1/2 xij minus mu j yj squared over sigma squared, right? So that's just the formula for the Gaussian distribution. And so what I'm saying now is that the mean depends on the class and also on which voxel you're looking at. Some voxels are just more active than others. The variance is just independent of absolutely everything. It's fixed and given. Okay? So I'm not going to go through the math for this. It would actually be a good understanding check for yourself if you want to go through what the classifier winds up looking like under this assumption, right? What you would wind up doing is you'd take the difference in the log probability, right? So you'd take log of p of xij given, let's say, plus one class, right, minus p minus the log of the probability of xij given the other class, call it minus, right? And you'd compute that, and from that you'd be able to calculate the separator. And just to give away the punchline, it turns into a linear separator in this case as well. And the only difference is that the input features, instead of being binary, they're real numbers. They're the activation of the brain tissue within each voxel. Okay? Yeah?
So it's worth pointing out that you don't always have to assume the variance the same for all classes.
Mm-hmm.
For example, in the homework, we're not doing that.
Ah, okay. So just to get that on the tape, we're not assuming the variance is the same on every class in the homework. And so you get a different sort of classifier in that case, and you'll see it on the homework. So any questions about Gaussian naive Bayes?
Why do we know that the Gaussian distribution is a good fit? Has it been experimentally verified that?
Right. So the Gaussian distribution, we're not actually really assuming that the Gaussian distribution is a good fit. What we're assuming is that the linear discriminant is a good classifier, and that this is a decent way to get a good linear discriminant. So the Gaussian assumption is usually false, but still useful. So this is a decent classifier even for data that's not perfectly Gaussian.
But then if you're taking the wrong probabilities, how does it end up with the right discriminant?
Right. So the question is, if you're making all of these false assumptions, why is anything useful happening? And that's an excellent question. The answer is the usual unsatisfying answer for theory, which is that you do a bunch of theory under a bunch of restrictive assumptions, and then you apply that theory when those assumptions are false, and cross your fingers and hope that everything works, right? And I don't know why that strategy keeps working, but it does, right? Probably what's happening is that we're, this same sort of theory, this math, is actually valid under weaker assumptions, and we just have to do harder math in order to prove that, right? So it's a reasonable heuristic to do theory under false assumptions, and it gets you papers. Right? All right, any more questions? All right then. So how does it work? If you do it on the specific case of trying to read people's minds, for a 2-answer question, you get a typical accuracy of 80% or a bit higher, which is not 99%, but it's a heck of a lot better than 50%, which is what you'd expect from chance, right? And actually, it turns out that it's easier to read some people's minds than others. I'm not going to speculate about what causes that. But some subjects you can actually get into the 90s on answering binary questions like this, which is kind of cool. The other thing that's kind of interesting, and you can see in this paper right here, right, you can see a lot more about what they actually did. It was important in order to get good accuracy to do feature selection. So this is something that we mentioned before, that when you're trying to combine information from a lot of sources, the lack of independence winds up making it difficult to combine information. And so it winds up that it's a good idea to do something to try and get your probabilities not to be so crazy close to 0 and 1. And one thing that you can do to do that is feature selection. You try and throw away the goal of feature selection is basically to to keep only the best possible features. And one thing that you could do is try and throw away, out of lots of highly correlated features, you could average together a bunch of them, or you could throw away all but one of them, and that's going to make your probabilities better, right? Because it makes the independence assumption closer to being satisfied. What they actually did here was kind of cool. They did a tiny little Gaussian naive Bayes classifier for each 3 by 3 by 3 cube of voxels in the brain. And if that classifier did well, they kept the center voxel as a feature. So they were using spatial locality, which is something that happens to be true of brain tissue, as a heuristic to help them do feature selection. But they did a bunch of different feature selection methods, which took advantage of different amounts of information. And they tried a bunch of classifiers. And the best one that they were able to get was Gaussian naive Bayes with this form of feature selection. Okay. Yeah?
Did they train on certain subjects and then attempt it on others?
No, they trained within subjects. So they trained on some trials of a single subject and tested on other trials of that same subject. It would be actually a very interesting question to try and map, let's say, my brain onto Alex's brain and see what the corresponding parts are, or even if there are any corresponding parts, who knows? That they didn't try and do that there. That's been the subject of a lot of research as well, is the mapping one brain onto another problem.
How do they account for the fact that rather than training a classifier, you were training your subject?
Right, so it's one classifier per subject, and they are training one classifier per subject. So the goal is, with experience on this one subject, can you read that subject's mind later in the, tomorrow or next month?
Well, no, but that's what I'm asking is, how do you know you're not training your subject's brain to work the way you want every time you put in your MRI? In other words, you're assuming that the subject is not changing from test to test to test. If you keep testing them over and over again, you may be training your subject, not your data.
Right. So the question is, how do you know that the subject isn't changing? And I guess the assumption is that it's difficult for the subject to change the activity of different parts of their brain intentionally and without feedback. But you're right, that assumption could be false. The subject could be changing. That might actually explain why some of the subjects were better than others. I think some of the subjects might have been authors of the paper, in which case they were motivated to have the classifier do well. But I don't know how they could possibly have trained themselves to be easily classifiable. But it is definitely a possibility. Maybe actually, let's see, if I were going to try and train myself to be easily classifiable, I'd try not to think of irrelevant things, right? I'd try to actually think as much as possible and as purely as possible about the words that I was being given. I think it's still interesting if you can classify even in that easier case. But you're right, the subject can be modifying themselves. All right, other questions? All right, so let's go on then. So now we're going to take a look at a different classifier called the Perceptron. And a Perceptron is, again, it's for the same sort of problem. So we have examples xi, right, which are real vectors in d dimensions. So you could have binary features, but it doesn't matter. So let's just assume real valued features. And then we have class labels, yi. And right now, for convenience, we're going to have them be in -1, 1 as opposed to 0, 1. Doesn't matter, right? As long as there are two classes, we can label them anything we want. Okay? And so the spam filtering problem that we looked at before is a good example, but so is the brain classification problem. Here we're going to think about character recognition as our main example. And so, for example, we might try for a binary classification problem to try and decide whether we're looking at a 4 or a 9, right? And I picked those two because they look kind of like each other. So they're not necessarily the easiest class to tell apart. And just a historical note, which is kind of cool. This Perceptron algorithm was first implemented in 1958. And if you think about what computers looked like in 1958, right, it had to be pretty interesting how they got it to work. And it turns out they built special hardware for it. And the hardware stored the weights of the perceptron, the adjustable weights of the perceptron, in variable resistors, which are better known as dimmer switches, right? So you have these like little knobs that you turn for the to change the weights in memory. And the weight updates, they had little servo motors turning the dimmer switches, right? So this is really old school, right? This is like one of the first machine learning algorithms ever. The input was a 400 pixel CCD camera, which I think was a 20 by 20 array of 1 pixel cameras. And so you took a huge card with the letter that you wanted to classify on it, and you put it in front of the camera. And this thing, you'd listen to the whirring of the motors, and this thing would come out with an answer. So I hope you guys don't decide to implement it this way, although I guess major points if you do. That would be pretty cool. But it's much easier to implement these days than it was back then. All right, so we're going to start simple. Let's suppose that our data is perfectly linearly separable. What does that mean? So we have a bunch of pluses over here. We have a bunch of minuses over here. And linearly separable just means that there's a line that has the pluses on one side and the minuses on the other. In other words, there are no mistakes. If you know the optimal classifier, then you're going to be perfect, right? And this is obviously not the best assumption in most cases, but let's go with it. And so suppose that we know that the data set is perfectly linearly separable. What the perceptron people ask themselves is, what would be the algorithm to find this linear separator, assuming one exists, right? So Gaussian naive Bayes, it might find the separator, but it's not guaranteed to, right? You can come up with examples, I think, where it won't. And so how would we design an algorithm that's guaranteed to find the separator in this case? So let's start off, we're going to derive one. And let's start off by simplifying our notation a little bit, right? So we had xi was in RD, right? And we're going to assume that the last component, x sub I comma d, is just equal to 1, right? And if that wasn't true, we can just add a 1, tack a 1 onto the end of every one of our examples, set d equal d plus 1, and then it was true, right? So I'm going to assume we've done that, and d is the extended dimension of our examples after we've tacked a 1 onto the end of each one. And what does this let us do? So let's say then that we're going to take our weight vector and we're going to change it. It will be W old plus the vector 0, 0, 0 up to b, right? So we had before our linear separator was xi dot W old plus b is greater than or equal to 0, right? So this was our separator. I should say, by the way, this is a compact notation compared to what we had written before, right? So what we wrote before was that sum over the features j of xij times W old comma j, right? Plus b is greater than or equal to 0, right? So this dot product is the same as this sum over components, right? And then we also use the notation, the inner product between xi and w plus b is greater than or equal to 0, right? So these three notations are all completely equivalent. This inner product is the same as this dot product, is the same as that summation, right? And I'm going to be using this notation for this lecture, but I just wanted to point out so that everybody was not confused, right? So we have, so we have now a vector of all zeros and then b, right? And so now w dot xi is equal to w old plus 0, 0, 0 all the way, right? A bunch of zeros and then a b dot xi, right? Which is equal to w old dot xi plus, and then b dot xi, right? I'm using linearity of the dot product, so it's w old dot xi plus 0, 0, 0 b dot xi. And that last thing, we know that the last component of xi is 1, and so that's just b, right? And so what we've done by tacking on this extra 1 is we've allowed ourselves to simplify our notation, and we can consider classifiers only of the form w dot xi is greater than or equal to 0, right? So we can drop the intercept term. Okay? Make sense? I see a bunch of nodding heads, so that's good. The other thing that we're going to do is that we're going to define ui is equal to yi times xi, right? So yi is either plus 1 or minus 1, and xi is a vector in Rd. So ui is also a vector in Rd. And what we've done is we've just flipped the signs of all of the negative examples, right? All of the examples with class minus 1. Why is that useful? Well, what we wanted was xi dot w greater than or equal to 0 if yi is equal to plus 1, right? We always, this by the way was, we want that if and only if yi is equal to plus 1, right? And what we want is xi dot w is, actually what we'd really like is for this to be strictly greater than 0, right? So that we know it's not on the boundary. And we want this to be less than 0 if yi is equal to minus 1, right? And so, well, ui dot w, right? If yi is equal to plus 1, then this is going to be equal to xi dot w, and so it's going to be bigger than 0, right? And ui dot w, if yi is minus 1, well, it'll be minus xi dot w, so it'll also be bigger than 0. And so with this notation, we just want to get ui dot w bigger than 0 for all I, right? So now we've simplified our notation a bunch by getting rid of b, we don't have to worry about b, and by getting rid of the two different classes of examples, right? We just want to make ui dot w bigger than 0 for every example I. Okay? So now we have ui dot w bigger than 0 for all I. And we can get our first algorithm, which is linear programming. So linear programming, we're almost here, right? If this were here, were a greater than or equal to instead of a greater than, it would be a linear program, right? It would be a whole bunch of linear inequalities. So we could just hand our problem to some linear programming software like Cplex, go out for coffee, come back, and we'd be done, right? So first, is this distinction really important, right? Does it matter that it's greater than 0 strictly as opposed to just greater than or equal to 0? Can anybody think what would happen if we gave the problem ui dot w is greater than or equal to 0? What happens if I give that to Cplex? That's right. You get the trivial solution w equals 0. So it does actually matter that we want a strict inequality as opposed to just plain inequality. So, yes?
If you also set it to 0, wouldn't that mean that you have the potential of having some of your items be on the line itself and then unclassified?
Right. So that's what happens. That's what happens when you get back w equals 0, right? If you allow some of your items to be on the line, then it says, well, just make them all be on the line. I can do that really easily. I probably started my optimization from w equals 0. I do 0 iterations, very efficiently give you the answer that you asked for, but not the answer that you wanted, right? So, what if we knew epsilon, which is equal to the minimum over all I of ui dot w, right? And by assumption, that's strictly greater than 0, right? In other words, everything is linearly separable, right? That's what it means to be linearly separable. Yeah?
Can you write your letters a little larger? They're kind of hard to see from that.
Sure, I'll try and write bigger.
Thank
So this says epsilon is equal to minimum over I ui dot w, and we know that epsilon is bigger than 0. So if we knew that, then what we can say is we can ask for ui dot w is greater than or equal to epsilon, right? And we know that that's not going to be violated by any of our examples. And this is strictly greater than 0, so it implies what we want, right? And we want that to be true for all I. And so we just hand that to Cplex instead, right? OK, so that's if we knew epsilon, right, which we don't. So what do we do instead? Well, what we're going to do is we're going to define v equals w over epsilon, right, which means that w is equal to epsilon times v, right? And now what we're going to do is we're going to throw in ui dot w is epsilon v is greater than or equal to epsilon, right? This cancels, and we have 1 for all I, right? And so what that says is that now we can find v, which is a vector in the same direction as w, even if we don't know epsilon, right? And we can do it by handing it to a linear programming package. And that's kind of cool because actually it doesn't matter what the scaling of w is. Right? It's the same linear separator. If ui dot w is bigger than 0, then so is ui dot 3 times w, or 17 times w, or Planck's constant times w, right? So, so that's great, right? This is kind of a cool trick. We didn't know what the separation was, but we just threw in 1, and it got us a multiple of the thing we wanted. So remember this trick. It's gonna wind up being useful in other classifiers as well. Yeah. Yeah, so the epsilon here it's just defined by this, this relation, right? It's just the smallest ui dot w for any example I, right? And so what does that mean? For each of my examples, I go and I compute ui, which is yi times xi, right? And I compute the dot product with the w that I want to find, right, which I don't know. That's why I don't know epsilon. Right? But if I did know the correct w, I could compute the dot product and then just take the minimum over all examples. And so, go ahead.
Why do you need this value?
Why do I need it? So if I knew it, right, I could then put it in to these constraints, right? And these constraints are inequalities rather than strict inequalities. And so it allows me to convert to ordinary inequalities instead of strict inequalities. Right? So the question was, why does epsilon help? And the answer is that it lets us convert from strict inequalities, which the software can't handle, to ordinary inequalities, which the software can handle. Okay. Okay, so that's our first algorithm for linear for solving perceptrons. This is not the algorithm that they implemented in 1958. They implemented a much, much simpler algorithm, which is actually just kind of pretty. So this is what's called the perceptron algorithm. And we're going to analyze it in the case of an infinite stream of training examples, right? So this is what's called online learning. I get an example, I make a prediction on that example, I get charged if I make a mistake, you know, and if I don't get charged if I don't make a mistake, then I update my weights, then I see another example, right? So this isn't quite the same as the setting that we've been doing before, right? The setting we did before was we get just a big batch of training examples, we optimize on them, and we get a predictor out at the end. So the nice thing is that if we have a finite training set, we can turn it into an infinite stream by just sampling with replacement forever, right? I just pick a random one, look at it, put it back, pick another one out of the bag, look at it, put it back, and I can keep doing that forever. And all of the bounds that we're going to look at for the perceptron algorithm in this online case are going to turn into good bounds for the batch case as well by what's called an online to batch conversion. We're not going to cover how to do that. I'm just going to ask you to trust me that they turn into good bounds that way. All right, so the perceptron algorithm is really simple. We start with w equals 0, right? We just assign 0 to w. We get ui, right? So we get a training point xi comma yi, and we compute ui, which is just xi times yi, right? And if we satisfy this inequality, then we're good. We don't do anything. We don't get charged for a mistake, and we don't update our weights because why mess with success, right? If we do make a mistake, then W gets assigned to be W plus UI, and then we go back and repeat. Right? So really, really simple algorithm. You can imagine it's the sort of algorithm you could implement with servo motors and dimmer switches, right? And the interesting thing is that it's actually a pretty good algorithm. And we'll show that in a couple of slides. But for now, any questions on what the algorithm is? And I should mention, why might we think this would work? Well, suppose that we now compute UI dot the new value of W, right, which is W plus UI. That's equal to UI dot W plus UI dot UI, right? And that is strictly greater than UI dot W, right? And so the new value of the weights is going to do a better job at classifying, right? It'll give you a higher value than the old value of the weights, right? So if you made a mistake on this example, you just move the weights so that you are slightly less likely to make a mistake if you get this example again. So that's why you might think this would work. Yeah?
So can this converge if you're so if you change the weight, you affect other data points?
Right. Right. So the question is, could this oscillate forever, or is it going to converge? And in the case of linear separability, it will converge. We're going to prove that. In the case that things are not perfectly linearly separable, it might keep updating W forever. And so we'll have to analyze it even without knowing that it converges. All right. So we're going to do an example. Let's see if I can get this example going. So let's see. All right. We'll make this big. OK. So people can see this OK? All right. So what do we have here? We have, we started with our W. So W is over on this panel. And it looks like it's just some, it's some point over here. The x coordinate is a little bit lower than -1, and the y coordinate is a little bit higher than -2. It turns into this linear separator, right? So the separator is W dot xi is bigger than or equal to 0. And here, what I'm showing you are all of the non-1 components of xi, right? So I'm showing you only the xi is 3-dimensional. And I'm showing you the first 2 components, and the last component is 1. And the last component is the color coding, right, of the class is the color coding of the points. Okay? And so the example that I selected at random is this one with a box around it. And it turns out that it's on the correct side of that plane, and so it's not going to do anything. Okay? Doesn't update at all. I'll select another one. Now it's on the other side of the plane. And so what we're going to do is we're going to update W. And we're going to, that's going to correspond to a change in where the decision surface is, right? And the way we update it is, well, if you look at this vector, right, from the origin to this example, this is a negative example, and so we're going to negate that vector. It points that way. And so we're going to add that to the weight vector, right? And again, I'm only showing you the first 2 components of the weight vector, right? All right, so we keep doing that, right? We select another random example. This time it got the positive example wrong, and so it's going to update the weight vector again. Turns into this decision surface, right? And if you look at it, this decision surface correctly classifies all of the examples, and so if we keep going, we just select things forever, and it's not going to change anymore, right? So that makes sense. I'm going to, I'll stop it and run it again, right? So here we have the example, which is correctly classified. We made a mistake and update our weights, right? We get another correctly classified, and it looks like I can't tell whether this one is actually correctly classified or not, but once we select it, oh, well, we're going to, yeah, so we're going to update there, right there, and now we have one incorrectly classified example here. We keep going until we select it, and now we're done. Right? Make sense? Okay, cool. So you can run this demo yourself, and you can look at the code at that link. Right? It's just MATLAB, and you know, hand it to MATLAB and see what happens. So before I go any farther, I wanted to mention a concept that kind of makes sense intuitively from looking at the picture, but it's an important concept, so I wanted to mention it. And that's the difference between example space and weight space, right? So I'm showing you here example space. It's just a plot of the examples. I'm leaving off the last component because, well, it's always 1, and so there's no point in plotting it. And then the weight vector here, right, I'm plotting in weight space. And so a point in weight space corresponds to a hyperplane, right, a decision surface in example space. Okay? And that's what we might often say, that these two spaces are dual to one another, right, in the sense that a point in one corresponds to a surface, a half space in the other. Okay? And it actually goes the other way, too. So each one of these examples corresponds to a constraint on the weight vector, right? And what does that constraint look like? The constraint is that the weight vector dotted with the example is bigger than or equal to, well, is bigger than 0, right? Strictly bigger than 0. And so if we I can't actually draw them because I haven't drawn the full 3-dimensional surface here, right, the full 3-dimensional space here. But if you take these examples, you can turn them into constraints on the weight vector. And so the idea of the perceptron algorithm is to keep trying to move the weight vector until it satisfies all of these constraints. And there's some polyhedron in weight space that is the set of feasible possible weight vectors. Okay?
I didn't understand the mapping which you said between the weight space in the sense that that one point wants to full length.
Right. So we have our constraint is that ui.w is bigger than 0, right? And so if we hold w fixed, corresponding to a single point in weight space, then there's going to be the examples that satisfy this and the examples that don't satisfy this. And so we're going to divide example space into 2 pieces. Same thing if we hold the example fixed and vary the weight, right? There are going to be weights which correctly classify this example and weights that don't. And so we're going to divide weight space into 2 pieces. Okay? Yeah?
Do the examples map to a line in the weight space?
Yeah, they'll map to a surface in the weight space, right? So I'm not drawing it here because the surface is 3-dimensional, right? This is a 3-dimensional weight space. Actually, what I could do is draw the intersection of the surface with the plane where you set the last component to 1, but that Yeah, that doesn't make so much sense. So it's harder to draw in weight space. I'd have to draw the real three-dimensional weight space in order to make it look good.
So basically, in the three-dimensional space, you are looking for a weight vector that satisfies all these constraints. Could we do a learning algorithm on the weight space like that? And
That is essentially what that linear program does, right? It's an optimization over the weight space to try and find a weight that satisfies all of these constraints, right? So that's the most explicit mapping of that to an algorithm. The perceptron is actually also, you can think of it that way, right? It's just updating its weight vector through a randomized algorithm until it happens to satisfy all of the constraints. Okay? Yeah?
So the plane that you get in the example space, though, depends on the ordering that you use of your example. So if, say, that the x that you have by the 0 isn't there, and your plane had shifted farther up, so we wouldn't have included that point, but it's not in your example space. So now if you try and use it, and you added that x, would you get the wrong answer?
So the question is, doesn't the answer that you get for w depend on the order that you present the x's? And the answer is yes, it does. And so when we analyze the perceptron algorithm, we're going to have to be robust to whatever order we present the x's in. All right? All right, so let's start analyzing. And in order to analyze the perceptron algorithm, what we're going to do is analyze it in terms of this idea called a margin. So I have some examples, plus, 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 minus, minus, right? And let's say the origin is here, right? And so when these are xi and yi, xi, comma, yi, right? I'm going to transform them to ui, right? And so I'm going to get my, So I'm going to get my my plus, plus, plus stay the same, right? But my minuses flip, and so they're going to wind up being about here and about here, right? So I should point out, by the way, this is not homogeneous, right? In order to draw things in 2 dimensions and keep it interesting, I'm going to use non-homogeneous examples. But in fact, the perceptron algorithm works fine with non-homogeneous examples as long as you don't care about learning the intercept term, right? So the only reason that we care about homogeneity is if we want to interpret one of the components of W as our intercept, but the perceptron doesn't care, right? It'll work just fine with any examples that are linearly separable. All right, so let's draw a sphere now centered at the origin. That's approximately centered at the origin around all of our ui, right? And let's just assume we know a bound on the radius of that sphere. And for now, just to keep notation simple, this is radius 1, right? So if it was some other bound, we'd just divide by that, and everything would be OK, right? But for simplicity, let's just say that the radius is 1. All right, so there's going to be a bunch of different, so all of our w's correspond to hyperplanes through the origin, right? So this is one possible weight vector, right? This is another possible weight vector, right? I'm going to go with this weight vector, right? Which is, somehow you think it's a good one, right? Because it passes as far as possible from all of these examples. And so what is, right, so I'll draw a dashed line right here, right? So these 2 examples are both equally close to this hyperplane, right? This distance here, it's the same for both of these examples. And what is that distance, right? Well, the orthogonal distance from a point to a plane, if you happen to remember the formula, it's going to be ui dot w over the norm of w, right? And so let's just choose w so that its norm is 1, right? And so then it's just ui dot w, right? So this was the quantity that we called epsilon a few slides ago, right? It's the, so this is a geometric interpretation of what epsilon is. It's the distance from the closest point to the decision boundary. Okay? So you can imagine that it's an easier classification problem if there's a big margin, and a harder one if there's a very small margin, because there's just a tiny set of W's that's actually going to work for you. And so we're just going to define the margin to be epsilon is equal to the maximum over all W such that the norm of W is equal to 1, right, of the min over examples I of ui dot W, right? So for the best weight vector, for the worst possible example, how close is that example to the weight vector? Okay? And so this quantity, epsilon, is dimension independent, right? It doesn't depend on D, the dimension of the U's or the W's. And so that's kind of interesting, right? Perceptrons could potentially work really well in high-dimensional spaces as long as we have a large margin, which is kind of interesting, right? Because there are a lot of machine learning algorithms that just totally break in high-dimensional spaces. But this is not one of them. So in the worst case, gamma could be really small. Well, I guess in the worst case, sorry, epsilon could be really small. In the worst case, it could be negative, but we're explicitly assuming that away. Even if we assume it's strictly positive, it could be exponentially small in the bit length of the examples that we give it. But what we're hoping, right, is that we are seeing a problem which has a large margin, and then that's a good reason to use the perceptron algorithm. All right, so let's go do the proof. Yeah. So the perceptron algorithm can work well in a high-dimensional space, right? If the examples are very high-dimensional, perceptron can still work well. There are a lot of machine learning algorithms that... Oh, why can it work well in a high-dimensional space? Because this quantity epsilon here is dimension independent. D doesn't appear anywhere in that definition of epsilon. And so we're going to analyze the perceptron in terms of this value. And so our proof is going to be independent of what the dimension of the examples is. It's going to depend only, once you hold the margin fixed, it's going to be independent of the dimension. Okay?
It depends on the W depends on the dimension of the data space.
The optimal W depends on the data, right?
Yeah, the dimension.
The dimension of W depends on is the same as the dimension of the data, right? But this quantity epsilon doesn't depend on what the dimension of W or U is, right? It just depends on their dot product, right? So if you fix the margin to be some certain value, it's gonna work equally well independent of whether you got that margin from 10-dimensional examples or million-dimensional examples. All right. So here we are. OK, so I'm calling the margin gamma in this slide instead of epsilon. Hopefully that's fine. I'll just write was epsilon. So we're going to pick W star, right? We're just going to call this unknown W star to be something that has the desired margin and has length equal to 1, right? And what we're going to do is, so we know W star doesn't make any mistakes. We're going to analyze our number of mistakes that we make by comparing to W star. So on every update, right? So if we make a mistake, right? Our new weight vector, W new, is going to be we're going to look at its dot product with W star, right? So why would we care about that? Well, the higher the dot product is with W star, the sort of more we've gone in the correct direction, right? So we're going to look at that dot product with W star. And so that's going to be equal to the original W plus ui, right? That was the update we made, dotted with w star, okay? Which is equal to w dot w star plus ui dot w star, right? And by assumption, ui dot w star is at least gamma, right? Because every example that we're going to see has margin at least gamma, which means its dot product with w star is at least gamma, right? So this is greater than or equal to w dot w star plus gamma, right? Which means that the whole thing, we always have that w dot w star is always greater than or equal to gamma times the number of mistakes we make, right? And the reason is that w dot w star, well, w starts at 0, so w dot w star is 0. Every time we make a mistake, it increases by gamma, and so w dot w star increases at least at the rate gamma times the number of mistakes we made. That make sense? Cool. Okay, so w dot w star is increasing. What about, we're going to take a look also at the norm of w, right? So actually, we're going to look at the norm squared of w. Why is this interesting? Well, I guess one way to think about it is the bigger the norm of w is, sort of the more examples we've seen, the more mistakes we've made, right? Because the only way for w to get big is to add a lot of stuff to it, and the only time we add a lot of stuff to it is when we make mistakes, right? And so what we want to do is bound how big w star can get. Sorry, how big the norm of w can get. So how is that going to update? Well, let's see. W new dot w new, that's equal to w plus the original w plus ui dotted with the original w plus ui, right? Which is equal to w dot w plus 2 ui dot w plus ui dot ui, right? So we only update when we made a mistake. We make a mistake when ui.w is less than or equal to 0, right? And so this whole thing is then less than or equal to w.w plus, this thing goes away because it's less than or equal to 0. And then we assumed that all of our examples were in a sphere of radius 1, so ui.ui is less than or equal to 1, right? And so what that means is that the norm of w squared is always less than or equal to the number of mistakes, because it starts off at 0 and it increases by at most 1 every time we make a mistake. Okay? So now we've bounded these two quantities. We can actually put the bounds together, right? So if we have the number of mistakes m times gamma, right? That's this thing here, is going to be less than or equal to w dot w star, right? Always. And then w dot w star, this is going to be less than or equal to the norm of w times the norm of w star, right? That's the Cauchy-Schwarz inequality. The dot product between two things is bounded by the product of their norm. The norm of w star is 1 by assumption, right? And the norm of w, well, we just got a bound here, right? The norm of w squared is less than or equal to m. So this is then less than or equal to the square root of m, right? Now we have m gamma is less than or equal to the square root of m. So if we divide through by square root of m and then divide through by gamma, right, we get square root of m is less than or equal to 1 over gamma, right? That's equivalent to this thing, right? And so m is less than or equal to 1 over gamma squared. So that is the perceptron convergence theorem. The total number of mistakes we make is less than or equal to 1 over the margin squared. Right? So that's kind of cool, right? It's a pretty simple page, a pretty simple proof. It fits all on one page. You get it by analyzing these fairly simple properties of the weight vector, right? It's dot product with the one true weight vector, and its length. Okay? So does anybody have questions on this proof? Yeah. That's right. That's right. So I suppose I should say, suppose there exists W star, which is unknown, but which has this property. Okay. Other questions? Yeah.
Actually, I don't get the double
So this first property here,
yeah, the first conclusion, the bound.
this one right here.
Yeah,
Right. So okay. So I'll go through that argument again. Right. So what we're going to do is we're going to try and figure out what is the new weight vector dot W star in terms of the old weight vector dot W star. Right. So the new weight vector is the old weight vector plus the current example. Right. Because we made a mistake. That's how we update the weight vector. So by linearity of dot product, that's W dot W star plus UI dot W star. Right. So the only thing then is that here, the assumption that W star has margin gamma, right, is exactly the same as saying that UI dot W star is bigger than gamma, right, bigger than or equal to gamma. And so we get, this is bigger than W dot W star plus gamma, right? And so we're updating W dot W star by adding gamma to it every time we make a mistake. So if we make m mistakes, then W dot W star is going to be greater than or equal to m times gamma. Okay? Did people get that?
So how do you get the historic norm of W?
So that's this one right here, right? So that I'll go over this argument again. So you have the new weight vector, the norm squared, right? It's just its dot product with itself. Again, every time I make a mistake, the new weight vector is going to be W plus the old one plus UI, right? So W plus UI dot W plus UI. You expand out the product, right? You get W dot W plus 2 UI dot W plus UI dot UI, right? So that's just expanding out the multiplication. UI dot W, right? We only update in case of a mistake, and so UI dot W is less than 0 to cause us to make a mistake, right? So I can just drop that, and then UI dot UI, I assumed that every example was in a sphere of radius 1, so this is less than or equal to 1, right? And so I get this bound. And so that means that, again, starting from norm 0, adding 1 every time I make a mistake, right? I get no more than m total.
So the initial value of the weight vector is all different.
The initial value of the, right, I assumed that the initial value of the weight vector is all 0. If you start at some other weight vector, there'll be a constant offset to this, and you'll get a very similar bound. Yeah?
we suppose we have a double star.
Mm-hmm.
So that means.
Well, we suppose it exists, right? We don't suppose that we have W star, but that there exists W star.
So that means the data are separable.
That's correct. We're supposing the data are separable.
So why do we care about the number of mistakes? I mean, we could finally have W such that you can make data separable.
Mm-hmm.
So the number of mistakes only happen when we use our algorithm.
Mm-hmm.
So
Right. So why do we care about the number of mistakes? So we assume that there exists a W star, but we don't know it, right? So we have to run some sort of an algorithm to find a W which is as good as this W star, right? And the question is, how long is this algorithm going to take, and how many examples is it going to have to see, right? And so what we're doing is we're putting a number of bounds, we're putting a bound not on the number of examples we see, but on the total number of mistakes we can make before we find a perfect separator, right? So that's why we care about the number of mistakes. It tells us that we're going to find this, this W quickly. Okay. All right. Yeah.
I'm sorry, I missed the stuff where, so after you have W dot W star and then you get factorial equal to W dot W star plus gamma.
Mm-hmm.
I followed that, but then on the next line.
Right. So this is true for every update that you make, right? And you only make updates when you have a mistake, right? The perceptron algorithm leaves your weight vector alone unless you make a mistake. So this, W new dot W star is equal to W old dot W star if you didn't make a mistake. And if you did make a mistake, it's at least W dot W star plus gamma, right? And so that means that when you sum over all trials, the mistakes and the not mistakes, W dot W star will be at least gamma times the number of mistakes, because it starts out at 0. It doesn't change when you don't make a mistake. And when you do make a mistake, it increases by at least gamma. Yeah?
So clearly there's a whole bunch of different perfect classifiers.
That's correct.
And is gamma somehow related to how many?
Yes. Well, I mean, there's infinitely many. So the question was, there are lots of perfect classifiers. Is gamma related to how many there are? And so the first, maybe not so helpful answer is, well, it's infinitely many, no matter what gamma is, as long as it's bigger than 0. But yeah, the volume of the region of perfect classifiers is somehow related to gamma. Gamma is the radius of the largest ball inscribed in the region of perfect classifiers. Question?
This isn't a proof question, but like with the example that you gave for character recognition,
Mm-hmm.
going from those characters to the examples.
Right, so the characters were images, right? And so you were looking at right, you had your CCD cameras pointed at the character. The CCD gives you a voltage depending on how much ink is in front of that particular pixel. And so you'll get 400 real numbers in a 20 by 20 grid, which is the amount of ink in each pixel of the character, right? So it's just a vector in R400, which is stringing out all of those pixels. You can think of each pixel as, let's say, a number between 0 and 1, which is, 0 is perfectly white and 1 is perfectly black. Yeah?
The radius of the ball, are we at the center of the ball, the W that we found?
Not quite. No. There's no guarantee that we're going to find a W that has any margin other than bigger than 0, according to this proof, right? So all that we're bounding here is the number of mistakes we make, and we aren't saying anything about finding W star. Right? So that's a good question, because in a slide or two from now, I'm actually going to start talking about, can we say that we find something with a good margin? But for now, we just find something that classifies all of the examples correctly with a bounded number of mistakes. Yeah?
So are there any ways of estimating what your margin gamma should be in order to determine how many points you need?
Yeah, so the question was, suppose you know how many points you're going to be able to afford. How can you turn that into something that says what the margin is that you're going to be able to classify, right? And so if you just invert this relationship, right, or maybe this one, start from that one, right? Just take 1 over each side. You get 1 over square root of m is going to be greater than or equal to gamma, right? And so what that means is that if you have m data points and your margin, does that make sense? Yeah, if your margin is, right. So this basically tells you, right, if you scratch that. So
That actually does work, because you're saying if you...
it tells you how many mistakes you're going to make, right? This doesn't say anything about how many examples you see.
Right, but you can't make any more mistakes than the number of examples. So if you get 100 examples, that means that the thing you do is, 10 square root of 10 mistakes, so you can set your gamma that way.
Right.
Because it may still be smaller, because if you don't make as many mistakes as you have points, then your gamma is even going to be smaller than that. It still is a value.
Right. Right. So the point is that basically you can invert this relationship. This is saying something about the number of mistakes in terms of what gamma is. You can invert it to get something about what gamma is going to be in terms of the number of mistakes, right? And then you can relate that to how much training data you can afford, right? But there's not actually necessarily going to be a monotone relationship between the amount of training data you have and the number of mistakes. All right. All right, so we're good on the perceptron proof? Yes? That's right. You find a perfect classifier after at most 1 over gamma squared mistakes, which is, it was a very strong assumption, right, that the data was perfectly linearly separable with a certain margin, but you get a very strong conclusion that you find a perfect classifier. Okay. Yeah.
So one interpretation could be that, so is this right when I say that if there are more mistakes, then the margin was small? So that
Right. Right. If you get more mistakes than this, right, then your assumption about what the margin was is wrong. And so that's, that can always happen. But this, you can also think of this as you can bound the margin that truly exists based on the number of mistakes that I've made.
So what I was, so basically if there are more mistakes, then your margin was smaller. So that was, so the way I was looking at it was because the margin was smaller, you are making more mistakes.
Mm-hmm.
Trying to learn it, and the other way around.
Right. Yeah, that's right. So if the margin's smaller, it's a harder classification problem. You're probably going to make more mistakes learning it. Although this is just a bound, you don't have to make more mistakes. The bound is worse.
So to put it more pointedly, you actually want to make all the mistakes very quickly early on such that you don't make mistakes later. And this has actually been a special case of what in linear and quadratic programming is called column generation. So you're basically creating instances where your current hypothesis is wrong, and you're trying to use these to correct your hypothesis, namely, what the separator should be as rapidly as possible. So the worst thing that could happen to you is if I give you all the mistakes at the very end, then you will waste a lot of time getting a lot of things right, and then only in the end you'll find out, no, actually you should have changed things.
Right. So just to get that on the tape, the goal is to make all of your mistakes early up front so that you find the correct W quickly. And this is an instance of what's called column generation in linear programming, where you think of this as you have a very large number of constraints on your weight vector, one for each possible example. And you're trying to find the ones that are necessary to force you to get the right weight vector. All right, one more. Yes?
What if the data is not linearly separable? Is there a sum result?
Right. So what if the data is not linearly separable? Does the perceptron algorithm do anything reasonable in that case? And the answer is wait a few slides, and you will find out. So that seems like a nice segue. I'm actually going to analyze, I'm going to say a couple of other things before I get to that case. And actually, we may not get to it until Wednesday morning. We'll see. This has been, it's a good proof, so it's good to go through it, but I had planned it faster. Okay, so this proof technique, the reason that I wanted to go through this proof is both because proofs are cool, but also because this is a proof that you'll see later again, right? So this proof technique is called an amortized analysis, also called a potential function proof. And it's a very useful style of proof. When is it useful? Okay, so we want to bound something, in this case, the number of mistakes we made. It's hard to get a non-trivial bound on the number of mistakes we make on any given trial, right? We know no more than one mistake per trial, but that doesn't tell us a whole lot, right? If we did know a non-trivial bound, we'd just sum up that bound over all trials and have a bound on our total number of mistakes. But what we want to do instead is make an amortized analysis. If we make a mistake, then it gets harder for us to make more mistakes later. right? And the way we count that is with this thing called a potential function. So a potential function is just this quantity, a real number, that we update over the course of our algorithm. And every time we make a mistake, let's say it gets larger, and every time, and then we put a bound on how large it can ever get, right? And so that doesn't say that we're not going to make a mistake on any one trial, but it does say every time we make a mistake, we're sort of borrowing from the future, right? Like, you know, that mistake keeps us from making more mistakes in the future. Okay? So how does this proof that I just did fit into that? So we picked a potential function, which in our case was the norm of the weight vector at step I minus the dot product between wi and w star, right? So this is interesting just because w star is something we don't know when we're running the algorithm. So during the algorithm, we don't know our potential. But during the proof, we can assume we know our potential and make anything, see what happens to it, right? So it's a proof technique that I can use, but it's not necessarily an algorithm to keep track of this potential.
The norm of wi squared?
No, actually, so the question is, should it be the norm of wi squared? The potential that we're going to use that corresponds to the proof I just made actually is this one. It's got the norm of wi, and I'll show you in a couple of lines how that correspondence happens, right? So the proof, what we did last time was, on the last slide, was we put bounds on this potential, right? So we know, first of all, we know that qi is bigger than or equal to 0. Why do we know that? Well, w star has norm 1, right? wi dot w star is therefore greater than or equal to minus the norm of wi, right? And so wi minus the norm of wi is 0, right? So we used the Cauchy-Schwarz inequality to prove that the potential is always non-negative. And then we put an upper bound on qi, right? So we knew that wi was less than or equal to the square root of the number of mistakes, right? And then we knew that this was greater than or equal to m minus m gamma, right? Sorry, this is basically what we proved, right? And so what this square root of m corresponds to the norm of w, right? That's where the square root comes from. And then this compared to that was what we proved, the longer proof on the previous slide. Okay? And then we translate that to a bound on m, right? So we just took the qi out of the middle, right? 0 is less than or equal to qi is less than or equal to square root of m minus m gamma, and we inverted that to find the relationship between m and gamma. Okay? So that's what a potential function proof looks like. Let's just say that I will get to the margin perceptron next time because I don't think I can do it in 2 minutes. So that's all for now. Think about perceptrons. Think about your homework. Don't wait to start your homework.